In this video, we're going to do a guided practice to find the pressure of a gas. So in this case, we have our initial setup. We have an open-ended manometer. It has air inside it. There's air outside it. Gas just all around. Well, it starts with equal levels in our manometer, and then we're going to add some gas. And so this gas is going to move into our reaction. We're going to take it from a tank that was at higher pressure, and we're going to put it into our reactor flask. Well, the result is we're adding gas, so it's going to push the water level down on its side and up on the other side. What we're going to find is that it went from being equal to this height difference, and that height difference is 13.5 centimeters. The liquid in this case is mercury. So manometers are generally filled with mercury, not water, because, well, we don't need as big a height change for the same pressure. And so you can have room-sized mercury-filled containers instead of building-sized water-filled containers. Given the rise of this much mercury, what I want us to know is to find the pressure of new gas. So take a second, pause, see if you can find that pressure of the new gas. Well, let's think about it for a minute. We knew that originally our water levels were equal. So our pressure inside equaled our pressure outside. And it was purely gas. So we'll color code it. The white is the gas. The liquid started equal, so there was no difference from pressure due to the mercury. But at the end, well, the pressure inside of the original gas plus the pressure of the new gas, all of that has to equal the pressure of the outside. The atmosphere didn't change, but it also has to equal the extra pressure from the mercury. Because what are all the things pressing down on the outside? There is air pressure shoving this way, and there is mercury shoving down, trying to push the liquid around and up the other side. On the inside of the container, there's air, and there's our new gas. When that new gas got added, it pushed up the mercury and created an opposing mercury arrow. What we actually find is that rise is exactly equal to the new gas. The only reason mercury went up that tube is we were adding gas to the inside. So any extra on the inside had to be balanced by an equal amount on the outside. This is why the mercury only got 13.5 centimeters. That's where it balanced the inside gas, new gas. Well, then let's ask a slightly different question. What is my total pressure? Can we solve what that total pressure is inside? Well, yeah. I know what my original pressure was. We said that up at top today was 778 millimeters of mercury for its pressure. So there was 778 millimeters of mercury. And the rise in mercury was equal to our new gas. So that means there's also 13.5 centimeters of mercury, which we can convert. Remember that 1 centimeter is 10 millimeters. So really this whole thing becomes 135 millimeters of mercury. We'll add that together. 778, 135, 913 millimeters of mercury. There's greater pressure inside that manometer after we've added the gas than there was before. Despite that it actually expanded to take up more space, it's pushing against mercury, pushing back. And so it's not expanding enough to stay the same pressure. This can actually eventually lead to your glassware exploding. If you put enough extra pressure in, that mercury just keeps forcing its way back down, and eventually you could get to the problem where your glass can't take the increase in pressure. Luckily, we tend to make manometers small enough that that won't happen. If your mercury ever reaches the top, it just starts rolling out of the top, and then you don't get the weight anymore. But on some devices that are very large, this is actually a risk. You can overpressure and destroy your device.